Hello, I'll be deriving the Maxwell Stress Tensor. So, let's apply the Lorentz force. The force on a charged particle is the charge of the particle times its electric field plus its velocity cross the magnetic field. Okay? Now, say that this was a volume, so we would have some little dq is rho times dv, where rho is the charged or volume charge density. So substituting this in, we would have the force is equal to df is equal to rho times electric field plus v cross b dv. Okay. Distributing rho, we get rho times the electric field plus rho v cross b dv. But recall that the volume current density J equals rho times v. So inserting that in, and also applying, insert this guy here, and say that this is rho times electric field plus J volume current density, or volume current, or current volume density J cross B dV. Okay. So now I'm going to say that I'm going to denote this lowercase f as force per volume. So this is force per volume, so this is basically dF over dV. So essentially, this is rho times the electric field plus J cross B. Okay. Now, I can do some substitutions. I want to eliminate the charge density and the current density. So from Maxwell's equations, the divergence of the electric field is equal to 1 over epsilon sub naught times the charge density. Okay, and from Ampere's law with Maxwell's corrections, that the curl of B equals to mu naught J plus mu naught epsilon sub naught times dE dt, the change of the electric field with respect to time. So, solving for J, we get J. So we get J equals 1 over mu naught curl of B minus epsilon sub naught of dE dt. Similarly for the charge density, we get rho is epsilon sub naught, divergence of the electric field. Okay. So now, making a substitution of these guys to this equation, we can see that the force per volume is equal to epsilon sub naught epsilon sum up divergence of E times E plus 1 over mu naught 1 over mu naught the curl of B minus epsilon sub naught of dE dt cross B. Okay, so this is so we can actually, this is a pretty ugly expression, but we can actually, or we can, you'll see what I'm going to do later. So I'm going to say that I'm going to do this clever substitution. The time derivative of E cross B. Applying your basic vector calculus, we get dE dt cross B plus E cross dB dt. But from Faraday's law, so this is Faraday's law, that the curl of E, electric field, minus the rate of change with respect to time of the magnetic field. Okay. So now we can apply this. Let's see. So we can now say that dE dt, or not, sorry, dE dt cross B, solving for d cross B, is equal to d by dt of E cross B minus E cross dB dt. So now, by applying Faraday's law, dB by dt, substitute that with the curl of E. So, therefore, dE dt cross B is equal to d by dt of E cross B minus times minus gives you a plus, and we get plus E cross the curl of E. Curl of E. Okay. Right. So we can substitute this. Let me box this. So we can substitute this into dE cross B. So when you distribute the cross B, you can substitute this in. So turn this over. Okay. So the force per unit volume is equal to epsilon sub naught divergence of E times E plus parentheses of 1 over mu naught over mu naught the curl of B cross B, to distributing the cross B, minus epsilon sub naught times d by dt of the curl, or not the curl, but E cross B plus E cross the curl of E. Okay. I'm missing parentheses. Yes, I am. Okay. So it's pretty nasty. So we can try to simplify this. to f is epsilon sub naught. Epsilon sub naught. You can group terms together. Grouping everything with epsilon. Epsilon sub naught e minus e from here. If we get epsilon naught from here, of e across the curl of e minus minus 1 over mu naught of b crossed curl of b. Okay. Then we have minus epsilon sub naught of partial derivative with respect to time of e. So we can read it, e. Gotta squeeze it in, e cross b. Okay. So let's see. Okay. So in the second part, I'll go further on if more on trying to simplify the Maxwell stress tensor. So this is the end of part 1. Hope you enjoy. Like, favorite, subscribe, do all that good stuff. Anyways, signing off. So